Hello, class. I guess my plan to show you chapter 13 next week um, didn't really work since they did make some modifications on the syllabus and on the book as well. So I'm gonna be going over chapter 13, which is the last chapter, which is a very important chapter actually, linear regression and correlation. If you're going to be taking the second portion of statistics in MSc 3371, you're going to be seeing this again. Okay, so the thing that we're going to focus here is going to be the correlation coefficient, and also we're going to be looking at the linear equation, the regression equation, and we're going to be doing an interpretation of some of this, not necessarily the elasticity. I mean, I don't want to go into the formulas as usual. I don't want to confuse you. I do want to talk about predicting it with the regression equation. And if nothing else, make sure right here it's telling you starting on page 577. If you open the PDF, it's actually 585. Start where it says how to use Microsoft Excel for regression analysis. I'm gonna show you how to do that so you can skip these pages. But then you start right here, estimating the demand for roses. So they're talking about how to estimate the demand of roses by using linear regression. Okay, I'm gonna show you how to do this output, which as usual, there is a feature in Excel that it gonna gives you those information very quickly, and in this formulas over here. Okay, so let's go ahead and before I begin with anything, correlation. How do they correlate to each other? What does that mean? For example, if I tell you that it's summertime, okay, usually in summertime ice cream sales grow, so probably maybe shark attacks. And then he explains that both ice cream sales and shark attacks increase when the weather is hot and sunny, but they are not caused by each other. Correlation is not causation. They are caused by good weather with lots of people at the beach, both eating ice cream and having a swim in the sea. Okay, so keep that in mind. There was another example, same thing about ice cream sales and sunburn. It happens because of summer doesn't mean they cause each other. So keep that in mind. Correlation does not mean causation. We wanna know how one variable correlates to the other. Doesn't mean they cause each other. Okay. So what does this mean over here? Is telling you right here. If we were to draw a line here, is telling you that it has a, I would say, kind of a weak 80% and an 80% correlation coefficients going on over here, positive. Over here, if we draw a line, as one goes up, the other one goes down. So it's a negative. See the negative sign over here is a negative 80% correlation coefficient. Over here is showing zero. So we don't really cannot really determine what's going on here. And so on this one, it's really going in circles. It's not getting anywhere. I have a few more examples here. A strong positive correlation. As one goes up, so does the other one. This is a weak positive correlation because not all points are on the line, even though you still can determine some positive correlation over here. A strong negative, as one goes up, the other one goes down. A weak negative, okay, a moderate negative right here, and no correlation as we saw, or just like this circle over here. Another example, I love this picture. I'm going to put it on your discussion during the week. Do you see as the correlation changes from 1.0, which would be 100%, and minus 1.0 is minus 100%. As it goes, see, up, both go up, the correlation coefficients increase. When it gets to the middle where points are everywhere zero, and then when it goes, one goes up and the other goes down, see, it goes from minus and then all the way to minus 100%. Okay. Um, Then again, I don't want to spend too much time on the other formulas of this. So what I'm gonna do, I'm gonna get an example right here that is on your book about some exams, and then they also show you later how to do that with Excel. So example 13.5, it talks about a random sample of 11 statistics. Students produce the following data where X is the third exam score out of 80 and Y is the final exam score out of 200. Can you predict the final exam score randomly select student if you know the third exam score? So it's asking you right here, if I knew this score over here, could I predict this? Yes, definitely I could. And then they give you a graph, a linear regression graph. Well, just by looking and compare by the to the pictures that I showed you before, you would say this is a weak positive correlation. So can you see it here? You can kind of draw a line. The points are kind of everywhere. And then you ask yourself, how do they do this graph? And also, how can you confirm the information I'm just telling you? How can you predict the next one? Well, this would take me to the next part that use this example right here. Recall the third example, final exam, and here is they're giving you the equation, okay, that is going to come up from that graph. How did they get this equation as well? There we go. I'm going to put it over here. I did put already over here the values, okay. So the way you do this, select the data, and again, data analysis, go to regression, do okay. Your Y input Y range is the second column over here. Input X range is the first column over here. Are there any labels? Yes, over here. Confidence, let's leave it as standard, okay, for 5% alpha or 95% confidence level. You've done that too. We're gonna do the output over here, sure. And I want to mine standard residuals to determine outliers, which I'm going to show you how to do that as well. And do OK. And here we go. So didn't I just show you the equation they had right here for your intercept and your slope? This is where they got these numbers from. So this would be your slope, okay, which is going to change, therefore is dependent, okay. And then let's say, and then they say over here, and I'm gonna give you the graph too, so hold on. And then they say over here, we predicted the students who are in a 73, we were in a 179 on the final exam. How? Well, right here, 73, right? So if we put a 73 over here, and we apply on that equation over here in this format, it's gonna be equals to minus 173.51 plus for this value over here times 73, and I'm leaving out the digits, so I'm being very precise. It's a 179, or if you even modify the decimals over here, it's really supposed to be 178.89 for what I use. If I would reduce the decimals here, it would give you um, if I would just type here 173 minus 173.51 plus 4.83 times 73, then that's how they got that 179.08. Right here, does it look familiar? ANOVA. If I would ask you, if I would place a question in the format of a hypothesis, you have your F critical, and you have your F statistic. So you would be able to determine, right? A statistic. You would be able to return to determine, right? Remember, if the p-value, oh, if the F statistic is higher than your F critical, then what do you do? Then you reject, right? If I would give you a question, if I'll pose a question for linear regression in regards to hypothesis testing, you would be able to answer that one as well. Important things. Remember from the actual problem over here. Remember I told you this looks like a weak correlation coefficient, positive correlation coefficient. Okay, how can we confirm that? Let's go ahead and let's select this table again, and then we're going to insert a scatter right here. Okay, a scatter chart. Over here, let's change this axis to be like the book. 80, I believe, if you look now, and that's exactly the graph we have, right? Close it over here. That's exactly the graph we have, correct? Okay, now how to confirm? Well, first of all, over here, we have what is your correlation coefficient. This value over here, and this your zero coefficient of determination, which is also called the R squared. To find this value, all you do is to square this value. I'm going to prove here, square your correlation coefficient, and there is your value over here. Okay, since it's a square, it's never going to be negative, because if you do remember basic math, minus plus minus, it's going to be minus times minus is going to be plus, plus times plus is plus, and minus times plus it's minus, and plus times minus it's minus. So minus and minus is all going to be positive, which brings me to this point over here. Your correlation coefficient on this output will never tell you whether it's negative or positive. It's up to you to make the interpretation. Remember, like I said, it sees it's going up, so it is positive. If this line CMU was going down, it would be negative. Okay, so how can you confirm your R square? Click on the table and click on add trend line. Here is going to say linear. Go to the bottom, click on display equation, and click on display R square. Okay, here you go. You can move this. Oh, not the whole thing. Just want to move the little equation to make it bigger here so you can see it. Okay, so here you go. Your R square right here, 40.43, which also you could look as a percentage. If you look, it's only 40. The correlation only explains about 44% of the relationship. It's not really significant. Okay, so right here on this form, if on this equation, if you do remember from the book, here you go. Your intercept and your slope. Your intercept is negative, but not your slope. Okay. His slope is actually positive. Therefore, do you see as it goes up? It goes up. That's what it means. Okay. So, but it cannot really be explained forever. Eventually, you would be just extrapolation. You're not going to be able to explain with this equation. If I ask you for your independent value, you should be able to determine that. I just said your correlation coefficient. Is it significant? Why? If I ask you to predict an X value, if I ask you to put the equation in the form of linear regression, so it's actually going to be the other way around. It's going to be y hat is equals to minus 173.51 plus 4.8274x. Okay. If I ask you to interpret the slope, so as One goes up, as one goes up, you're gonna increase in 4.8274. Any outliers? If you do remember, outliers are determined by usually anything above 2.0. If I look at the standard residuals, the only one that sees here would be the first observation point, which your first observation point is this one over here. And then actually, if you look at your graph, this seems to be the most one. There you go. Let me add the data. 175 is the first one right here, 175. And you would be done with linear regression, and you would pick up on MSC 3371 as you're going to be presented. You just study the sum of the squares, the mean and square, and all that. So in MSC 3371 in forecasting, you're going to be determining the sum of the square errors, mean of the square errors, and this is all going to make a lot of sense. Okay, and that's all for this term.